So the study sets again are due by 6 o'clock. The worksheets due by midnight. I did want to mention that, you know, we all have those days. This class, it shouldn't be a problem because your worksheets are pretty straightforward. But if you have a time and I don't make that 11:59 that strict. If you're like an hour late at like 1 o'clock in the morning, sometimes Blackboard gets overwhelmed because there's a lot of 11:59 p.m. deadlines for a lot of classes, and it becomes really slow. So don't start panicking and sending me emails. I got a lot of emails. That's why I made this comment in the past semester, and students were panicking because it was 11:59 and it was just going so slow, and they were like, what do I do? What do I do? I also asked that you, especially if you're using an iPhone to submit, there were a lot of issues last term that the document wasn't submitting. Please make sure you always view when you submit that you can see it, and if you can see it, I can see it. I do try to always remember to set it so you can submit it twice. So if there was an issue with the submission, your lab is due by Saturday. You can absolutely do it before then. These first 3 labs, or the first 2 labs, are brand new. The second lab should be up there this weekend. So if you have big plans next weekend like I do, this lab has 3 parts to it. And so one part, I made a 30-minute video that's up there on the YouTube, and it talks about that. So one part is you're going to write about an innovation for water. I talk about several in the video. You can use one of the ones I talk about and look into it yourself, or you can just find your own innovation. And so like I say in the video, we all know what the problem is, that we've been polluting the water, the air, the earth in all these ways. And so I want you guys to find some cool way, or a way that we can use salt water. And then you could do a little bit of kitchen chemistry. Just a reminder, you have to take a selfie. Have fun taking your selfie. And again, you guys do have a limit. I don't know what I put the limit as, unless you're as clever as Christy and can figure out how to. There were actually several of you who started figuring out how to embed your fun pictures in there, but have fun with that. And then there is actually a last page that I actually walk through in the video, but you can try it, which is working with hydrophobic and hydrophilic, and that other word, which is the amphi, which is both hydrophilic and hydrophobic. Yeah, all right. So let's go through, this is the other thing I had to mention. So this is more for those of you who were from last term, and also for you who are new. So last term, it was really fun in the class. I randomly will ask questions in class, and if you answer the question, it's certain questions, I do keep track of your name, and I'll give you a bonus point. I am going to put a limit, so you can only get 2 bonus points a week. And so if you emailed and responded to my email, which a lot of you did, you already got a bonus point. So if you did that and your name's up here, then you have your 2 bonus points for the week. So you have to let somebody else get a chance to answer. All right. So we are on page 4. And if there's no questions about the syllabus, all right. We will get done early tonight, and then I'll stay after for a little bit for people who have questions. So we are gonna do, I'm laughing because I usually have 3 chalkboards to do this piece on, and I have this 1 piece of paper. So I'm limited to the space you all have. We're gonna do this thing where we're gonna make a whole bunch of zigzags. So this is just representing a carbon chain. It can be any length, it doesn't really matter. And we're going to put side groups on it. And butyl means how many carbons? And they all said 4. Yeah. So butyl means we have 4 carbon side group. Now the thing that's interesting, there's 4 ways you can make a butyl side group. And we're going to go through the 4 ways, and each one of them has a different name. And we're going to start running into them in these pictures down here. So your next homework set, you've got the basics, the ones I looked at a handful of your homework just briefly, and a couple of people were asking me about the worksheet. We start running into more, we keep building on this. And so that's why you have a study set every class. So we keep building and get feedback each class, and then we take the next layer and build. So if we do, let's do a different color. If we just do 4 carbons in a row, so 1, 2, 3, 4 as a side group, that would just be straight butyl at whatever number it's at. That's not that common. Now, what if we did 4 carbons in a row, but we attached at the second carbon? This is called sec for second dash butyl. Again, YL means it's a side group. So sec, because it's attached to the second of the 4 carbons, and then butyl. And I did want to draw this one a different way. That's the same thing. It's just bending the things in different ways. So that is a sec butyl also. So again, we have 4 carbons in a row, 1, 2, 3, 4. And it's a side group. All right, let's switch colors. Then there is another way we can do it, which is chicken feet. And I just realized I want to do these also where I draw the carbons out, which I do sometimes. This is tert butyl. So it looks like a chicken foot if we're pointing down, or I don't know. It is more commonly called just T-butyl. So that's a shorthand way. Everybody calls it T-butyl, but it stands for tert. And I've had some students say it looks like a turtle's foot. So if you want to think of it that way, it looks like, I've never seen, didn't know turtles had little things pointing out. If we draw the carbons, there's a carbon in the middle with 3 other carbons around it. This is why it's called a butyl side group, because there are 4 carbons sticking off. They're just arranged in a T. So that's the other thing. If you think of it, it looks like a T in T-butyl. If you show the carbons, well, what is our mantra? If you actually write the C, you have to show the hydrogens. So these hydrogens on the outside are CH3s, and the carbon in the middle already has 4 bonds. It has 4 carbons around it. So again, this is T-butyl. All right, we're going to show it another way. Same thing, same T-butyl. You could also show carbon and then put a parentheses, and your teacher is, and then put CH3 and then a 3. And so what the parentheses mean is this is the same thing we just drew. We're saying we have a carbon with 3 CH3s around it. I will tell you, students despise the parentheses. That would be a nice way of saying what most students' feelings are for parentheses. So we don't run into them on this page. I don't know if we run into them on the next homework set, but you can sit there and grumble and go, I really don't like the parentheses. You can come to office hours and tell me you don't like the parentheses. And we don't see them that much, but that's all it means. You can redraw it and show the carbons like that, or redraw it like that. All right, so that's 3 possible ways. So the fourth one is you're going to do, that's it. This is isopropyl. I'm sorry, isobutyl. So it's like an isopropyl with an elbow. So I had students.
Can you move your paper down? Sorry, it's just there. Yeah. Perfect. Thank you.
Yeah, thank you. Actually, yeah. I don't have as big a desk here. I had a student who made a tattoo of this one because they had a joke that the isobutyls were like your hand, you have an elbow and then a peace sign. And they actually had this joke and they were telling the whole class, and everybody in the class, nobody ever missed the isobutyl. So that's how you would draw it if you show it as sticks. It's kind of like the peace sign with an extra bend, or the antenna has a kink to it. If you draw it out, this is what it will look like, is it's a T, but instead of being attached to the center of the T, like we were here, we're attached to the outside of the T. Again, if we show the carbons, we have to show the hydrogens. So this first carbon has 2 hydrogens. This guy here, he's only got 3 bonds, so he's going to need 1 hydrogen. And then these on the outside, they're going to have 3 hydrogens. So that's another way. And then I'm going to make my chain a little bit longer. I'm going to show you one more possible way you can see it drawn. Again, this is isobutyl. This is why the colors are amazing. You can get more colors. I only have 4 colors. I don't have orange. Kind of sad. You may see it where it's drawn even like this with, so it's kind of like they turn the T sideways, but again, we're not attached to the center of it. So these are the same. The green ones are all isobutyl. Yeah. So with that, I'm going to pause my recording again, and I'm going to give you guys a chance to try drawing these two. So again, start with the end, the heptane or the pentane, and you can draw it. I will draw it both ways. You only have to do it one way. So you can do zigzags, or you can draw your carbons in. And then down here, do it with pencil or some kind of eraser. See if you can find your longest chains and name them. So I'm going to pause. And if you have to take a break, you can take a break for 5 minutes and just wait. So let's go ahead and draw them. And again, I'll draw them both ways. You've all probably already found a preference that you have for which way you draw. All right. So heptane. So 1, 2, 3, 4, 5, 6, 7. Again, numbering is really helpful. 4, 5, 6. So if you can't count like me. And then at number 4, we're going to have an isobutyl. So that has the kink and then the peace sign. So that's our isobutyl at number 4. And then at 2 and 3, we have a methyl. And so again, if you're doing the zigzags in a mountain peak, you point the side group up. And so that's what it looked like. If you want to draw it out with the carbons, 1, 2, 3, 4, 6, 7. So again, numbering, when you get more than 5, it's really helpful to number. I don't know, 7 it must be because it's such a funky number. Right, and we have a methyl at 2 and at 3, making your groups go opposite way, and then the isobutyl. You can also, this is a question that usually comes up about now. You can also do a mix. Like some people will like to draw the carbons and then do the kink for like the isobutyl. They're okay drawing like that. And then just make sure you put your lines in for your hydrogens if you show your carbons. And again, using different colors, totally legit. All right, on this one, pentane, so 5. And then in the middle, we're going to have an isobutyl. So let's draw that the other way, and then your teacher is like figuring I am par for the course because this is incorrectly named. So 5 carbons across, and then we would get this T shape, and you can write your hydrogens in however you like. That middle hydrogen there, sorry, middle carbon, no hydrogens, and then you can show your hydrogens as dashes, or you can write them in. This guy would only get 1 hydrogen. Just trying to show it different ways. And although this name looks correct, it is not, because you can get 5 carbons by starting here. 1, 2, 3, 4, 5. This was that rule I was trying to say with when we're going through the study set. If you can get a longest chain the same way, 2 different ways, you go the way that's going to give you more side groups. It's kind of a silly little rule. And this class is going to be all show your work. Your midterms are going to be like 90%, and the celebrations are going to be 90% show your work. And so there's part credit. So you would get part credit because well, not because I named it wrong, but if I asked you, if I gave you something like this and you named it that way, you would get most of the credit, but then you would have me telling you, well, yes, it is a pentane, but the numbering is, if you can get to 5 another way, you want to break it into more side groups. So it's actually a 3-ethyl. And I think I keep this on here every year to point out this rule, because we're going to run into it. We're going to run into it not that often. I think it shows up once on the study set. All right, so for naming, these don't go straight across. We're going to start 1, 2, 3. Our longest chain is going to go like that, and we get 1, 2, 3, 4. Yeah, so 1, 2, 3, 4, 5, 6, 7, 8. So that's also another thing I've shown for some students, using a color pencil and crossing out, making a line through your longest chain. I think that was something Vincent was doing on his pad. That's actually a really nice feature of the pad, because if you get it wrong, you can erase them. So 8 is octane. And so Ezra, this was a question you had asked me on the worksheet, and on the worksheet or the study set, I had answered you correctly. On this one, the dilemma is a little bit different. And if I started numbering in this direction, 1, 2, 3, 4, 5, 6, 7, 8, right? We still get 8, and I get my side groups at 4 and 5, no matter which way I go. And so if the side groups end up as the same number, no matter which way you go, the alphabet takes preference there. So the question you had asked me, and I can't remember what the problem was, the numbering did come out lower going the way that we had talked about. So this is the isopropyl, the side group. So we want it at the 4 because it starts with an I. And I forgot to tell you something with the butyls. This is good. And then 5-methyl. And so you can ponder that, and then octane. All right, there is something I forgot to mention up here with these guys. And isopropyl starts with an I, methyl starts with an M, ethyl starts with an E. If you use dis, tris, tetras, they do not affect the alphabet. They're just telling you how many you have of it. So you don't look at that for alphabetizing. With the butyls, this is really funky. Butyl starts with a B. Isobutyl starts with an I. Tert-butyl starts with a B. Sec-butyl starts with a B. And the reason is they're hyphenated. I did not make up these rules. I just have to embrace them as I teach them to you. So sec-butyl and tert-butyl start with the letter B when we alphabetize. And again, these are all small. They're little, small, tedious little things, but yeah, we got them. All right, the next one. So my longest chain is going to be, you could do 1, 2, 3. We could also do 1, 2, 3, 1, 2, 3. No matter what we do, this guy is going to be number 3. And then we're going to go down 4, 5, 6. So it is a hexane. And again, if you started at the top, you get 6, and going down, if you start this way and curve down, if you just go straight across, you only get 5, and that would be wrong. So you want the longest chain. These are both ethyls at 3, so it's a 3,3 diethyl. And you can also ponder what it looks like, what it was a clip art for, or not clip art, the stone art stuff. All right, this next one, we're gonna go straight across. And again, back to the question during office hours. This one, we do want to start here because we run into a side group at number 2. Although over here we run into an ethyl sooner, it isn't until number 3. So you want to start from the side in which you run into a side group first. If you run into it, it comes out the same, then we go to other rules. I don't know how to elegantly say these things. 7, 9. So no name. All right. It's where colors can be nice. So these guys are my ethyls, and so you can circle as you use them. So we have a 5,7 diethyl. Yeah, I guess there is a lot of forgiveness, and you have to keep forgiving me because my screen's not big enough. Okay, and then those are methyls at 2 and 7, so 2,7 dimethyl nonane. All right, and then that's connected there. If you're ever unsure, just ask. It's not really that big of a deal. That is why I wanted to also make a comment that for your celebrations, your midterms, they are going to be during the class time. And how I typically do it is the exam or the celebration post like at 6 o'clock, and you guys work on it. And I'm here on YouTube. I'm sorry, not on YouTube. I'm here on Zoom in case you have a question. And it is because there is frequently, like, you're not sure, is that carbon attached there? And so, and I do give generous time because I recognize in this environment, there's distractions that happen of all kinds of ways. The first celebration, I wanted to mention this just in case I have to make changes to syllabus, but is scheduled for a Wednesday in the 4th week. And I know there's at least 3 people who have a conflict on Wednesday. Some of you are working, and so we can just make sure the week before we touch base and we figure out when to do it, so everything's fair. And yeah, worry about that. That's not until the 4th week. All right, this is cyclohexane. And in a cyclo, a side group has to be, sorry, just please so sweetly tell me again if I'm off the screen because it's so unnatural. A side group has to be at number 1. If there's only one side group, it is at number 1, and you do not tell me it's at number 1 because it has to be at number 1. Number 1 can be at any position. It just has to be at a side group. So this is just an isopropyl cyclohexane. Is there any questions from this page? All right, so we're going to talk about isomers. And isomers are awesome. I love isomers, and so are you going to love isomers. That prefix iso, we saw this at the beginning of 104 when we saw isotopes, and then we saw it later on when we did isotonic. Whenever you see iso means same. And what an isomer means is the same molecular formula, so same number of carbons, hydrogens, oxygens, etc. But they're going to have a different arrangement, meaning a different name. They're going to end up with a different name. So there are some tricks to doing this, and this is a really fun game if you know the tricks. Don't count the hydrogens because you're going to get them wrong because there's so many hydrogens. Look for saturation versus unsaturation. If they're all single bonds, and you can tell they're all single bonds because there's no double bonds. If you have a double bond, these guys are unrelated. Because what happens when you get a double bond is you have to lose 2 hydrogens to be able to make that double bond. So the hydrogens are different. You don't have to tell me why, but you can write a note to yourself. All right. On E, I have a double bond, but I have a double bond there. So that's okay. It's not. So that's a real quick way to know if you have your hydrogens the same. So let's just walk through these, and it's just examples, and I'm pretty sure you have some examples like this in the study set, and we'll just keep running into examples as we keep building on this. On A, these guys are identical. They are the same. They are not isomers because they're the same thing. They are both butane. And this is again, these were supposed to be attached. It's just how I drew it. So this is 4, we're showing it 4 across, and this one's more, I was trying to show the zigzag. So they're the same thing. B, these are isomers. So they both have 4 carbons, and they both have 10 hydrogens. I can count the hydrogens without counting them physically because they're both saturated. They are not both called butane. The second one is called butane. The first one, so the naming system that I've been teaching you is called IUPAC, so the International Union of the Pathetic and Apathetic Chemists Society. I had some name, I don't remember what it was. My dad probably belonged to them, and my mom. I just don't join clubs. Except the Sherpanati. You guys are all part of the Sherpanati, so we have our own secret society. So this has a common name, which is isobutane. And I wanted to mention that for students like Melanie, because she's going into hazardous material management. And so a lot of times you'll find out there that things will have common names. We're not going to call it isobutane, but it's saying, hey, this is an isomer of butane. And so that's all it means, in case you run into that in reading stuff. We're not going to name it that. We're going to always go with the IUPAC. Well, not always, but right now we're going with the IUPAC. We find our longest chain, which is propane, and then we say there's a methyl. So here we go. Here's a bonus point question if somebody wants, can't be somebody that one Monday. Why don't I put a number on this one? It's just methylpropane. It is not 2-methylpropane. So why do I not put a number? It's a really good bonus question.
Is it because there's only one side group?
It is not because there's only one, but you're in the right direction. You have to take it like one more step.
Because the middle would be the only spot you could put it. You couldn't put it at the left or the right because that would create a longer chain.
Yeah, was that Jeremy?
Yeah.
Yes, Jeremy, you said it much better than I could have. If you move the CH3 to the number 1 or the number 3, you just made butane again. So the side group, the methyl, cannot be at number 1 or at number 3. It can only be at number 2. And so it's like a redundancy. So you don't say 2-methylpropane, you just say methylpropane. You can ponder that. Those are like, it's yeah. Awesome, Jeremy. It's probably because you took Chem 106 and had an awesome teacher. I don't know. All right, on C, count your carbons. So 1, 2, 3, 4 carbons. 1, 2, 3, 4, 5 carbons. So we have different carbons. These guys are unrelated. So just start there. I'm laughing because I don't know why they have different numbers. I'm the one who made the question up, but they're unrelated. The carbons are different. All right. So we did D. Again, they're unrelated because of the double bond, right? That double bond, that one doesn't. And then on E, we see a double bond. So that's going to make my hydrogens the same. We count our carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So they both have 5 carbons. They both have 1 oxygen. They both have 1 double bond. I put an X through my oxygen when I write it like that, so you don't think I wrote a 10. And everything's mixed up, meaning here I have a double bond between the carbon and the oxygen, and here I have a double bond between the carbons. A reminder, these hydrogens, we write it like that, but they're on the carbons, they're sticking off. This is just the condensed way. So these are isomers. This is a tough question, but it is, you guys actually, I'm sure you've got this. So count your carbons, you have 1 oxygen, count your double bonds, and then things are rearranged. We move the double bond. I want to do one more, and that is, let's do it with zigzags. So we got an F. So we got that, and we got that. So pentane and cyclopentane. So I'll give somebody else a bonus. Are they isomers, identical, or neither? And then you'll have to tell me why. So somebody new who wants to take a go at it? Nobody knows who you are, and I only ask who you are if you get it right. Anybody else want to try it for, oops.
Is it because they have a different arrangement?
They do have a different arrangement, but they are not isomers. They are unrelated. So does anybody see why they are unrelated? They both have 5 carbons, but they're unrelated.
Do they have different numbers of hydrogen?
They do. How do you know they have a different number of hydrogens?
Because one is a circle, so there's not extra hydrogens on the end of the chain.
Yeah, so when you close it up, it is still considered saturated. It's a cyclic saturated. But this one, remember, you just double the hydrogens because you lost the end hydrogens. And this one, we double the hydrogens and add 2. So Kaylee, that was kind of back to the question you had asked me today. Yeah. So they are unrelated. Now, here we go. We're gonna try this again. What if we do green? And we'll draw the carbons. We'll put a double bond there. So you can put your hydrogens in. At the double bond, you lose a hydrogen. These guys, they will be isomers. And this is what we're going to be doing in class on Monday. They're isomers because this one lost 2 when you closed it. And this one lost 2 when we made the double bond. So we'll run into that next week, but that's might run into that in the study set question for Monday also. All right, so we're gonna do this one together, and then I'll let you try this one, or you can jump ahead and try it. We're gonna do 4 carbons, and we're gonna see how many ways we can draw it. So you can draw the carbons. I'm gonna do zigzags, so we can do 4 across. We're gonna name it. There's only 2 ways we can draw it. So we can do butane. And we can do isobutane, which is again just methyl propane. So again, you can't move that. This is back to that question Jeremy answered. You can't move the methyl to number 1 because then you're naming it wrong. You're just back to this butane. So there's 2 different ways. It is to draw a 4-carbon alkane. So I'm going to pause. I'm going to give you a moment. I'm going to have you try and see how many ways you can do. You have 5 carbons. So basically you have 5 carbons and 12 hydrogens. How many ways you can draw it and also name it. So I'm going to pause. Will you guys try that? And here we go. So 5 carbons. You can do pentane. So that is always your first one, is just whatever number straight across. And again, you can draw the carbons. That's perfectly fine. You can do 4 with a methyl. This is back to Jeremy's thing. This is just methyl butane. If you want to call it 2-methyl butane, technically we do not put the 2 with it because it can only be at 2, because this is the same thing as that. These are both the same thing. I just flipped the diagram, right? Upside down. Look at that. I used to have the board and I couldn't flip it. They're the same thing. So if you're flipping it in space, if you're flipping it over on your paper and they're the same thing, that's not an isomer. So, and again, if you called it 2-methyl butane, I would just cross off the 2. I wouldn't mark you wrong for that, but we don't put the number, and that's only with the methyl. All right, my next choice is to go down to 3 carbons, and we just put 1 there. So, and then we put another 1. So it is a dimethyl propane. Both methyls have to be in the middle because you can't have a methyl on the end or you got it wrong. The question somebody will tell me is they think they found another one and they want to do ethyl propane. I say, why can't I do ethyl propane? And they can't do ethyl propane because they named it wrong. This is actually 1, 2, 3, 4. So we're back to that one. So again, this one would be wrong. Those are the only 3 ways. There are 3 isomers possible. And again, we can't make it into the cyclo because that would have a different number of hydrogens. All right, we're almost done. Isn't that wonderful? Oh, this is another really fun game. This is the Gnome Game. So I'm at my mom's, and so I don't have any gnomes. So we'll just have to play with the little teddy bear who's made of coal. I'll put him here instead. So gnomes love to name them wrong. So we're going to run into this game. So what you do is we start at the end with propane, and we draw, and I'll draw 3 carbons. And then at number 3, I'm going to make a sec-butyl. Now, you can do this with zigzags also. You can do it with carbons. When you do this game, you can leave your hydrogens off even if you show your carbon. Because I'm not asking you to draw it. That's not what you're being graded on. You're being graded on giving me the correct name. And so you want to make a sketch of the gnome name, which is incorrect. And now we're going to give it the IUPAC name, which means we'll start here. 1, 2, 3, 4, 5, 6. This is my side group. So I have a 3-methyl hexane. So for a lot of students, this can be easier to draw by drawing carbons, but you can also do the zigzags. That is the correct name for this one. All right. So I'm going to give you a moment to try the other 2 again, or at least try drawing your butane and your pentane. And he'll sit by the little kid with the lump of coal. And he doesn't know why he's unhappy. You can surround him with all the... It's great. It's why I lived in West Virginia also. And when we moved, I was in 2nd grade, and we decided right before we moved, we were going to walk in the woods further than we ever had. So, right, this is 7 years old. And so me and my brother and sister and our neighbors, and so we're all these little kids going on this big adventure. I mean, we really probably did not walk very far, but we walked a little bit further, and we ran into, like, I don't know if they saw us, but it was basically hillbillies who were basically just living there in the middle of the woods. And they had their moonshine still. And we, like, I think that's the fastest I've ever run in my life. We're like, ah, I'm running home. All right, let's go ahead and try this. And then we'll be done. All right, butane. You can draw it like this with your 4 carbons, and then propyl would mean draw it like that. So you can do it as sticks, or you can do your carbons 1, 2, 3, and then 4. And then at number 3, we draw a propyl. I want to remind you, propyl does not mean isopropyl. It means that you're doing 3 in a row, not 3 where you're attached to the middle. All right, either way you draw it. Here's my side group. So 1, 2, 3, 4, 5, 6. We're at the same name. Or up here, 1, 2, 3, 4, 5, 6. So again, it's a 3-methyl hexane. So those gnomes are extra mischievous. All right, pentane. 1, 2, 3, 4, 5. And then at number 1, we're going to do an ethyl. At number 2, at number 4, at number 5, we do a methyl. So they just, and again, if you want to do zigzags, at number 1, you would add an ethyl. You have to number 1 at 2, at 4, and at 5, you would have your methyls. So you can see their longest chain is they just missed it. So number 1 is going to be over here because I run into my side group faster. 3, 4, 5. There's my other side group. 6, 7, 8. So it is an octane. And I have methyls at 3 and 5. So you really can't trust the gnomes. They're very fun creatures, but they always name it wrong. And so we have to change the nomenclature into IUPAC nomenclature. All right, so we spent a lot of time this week with the basics and naming, the basics of naming. And so what's going to happen each week after this is we're going to add something. So next week, we're going to add double and triple bonds. And then we're going to start adding oxygens and double bonded oxygens and things like that. The naming gets easier in a lot of ways once we start doing that. What we're going to be spending most of our time in future weeks is it's going to change properties. So we're going to look today at the basic properties that these guys have so many uses. And I made an introductory video where I did a quick over looking at all the different functional groups that were like on the first page. And we'll be seeing each of those each week. There's going to be a video for next week's lab, which talks more about this, but there's 3 main uses for the alkanes. Anybody know? Probably their biggest thing, which is why Christy dressed up as a coal miner, is you get the lump of coal. Here's our lump of coal. These guys are our fossil fuels. They are called fossil fuels because they are what you and I are going to become when we become fossilized. Not us as in our spirit, but our physical body is made up of carbon, and it eventually, over thousands of years, the physical part of us is going to become hydrocarbons. So double bonds become unstable and everything eventually becomes the lump of coal of carbon. And so the fossils, the dinosaur bones, and stuff. So they're going to be used as fuels, which is what powers our cars, warms our house, things like that. They are also used as a building block for plastics and pretty much everything else. We're going to get into that. The video I'm going to make for your next lab talks about this a little bit. And they are also commonly used as solvents. A lot of things are non-polar. And so if we're trying to clean up like paint and stuff, so paint thinner is usually some kind of alkane or alkene or something. So we run into them there. But probably the biggest thing is the fossil fuels to heat and stuff. All right, boiling point. So as you increase the number of carbons, you increase the boiling point. So in this class, when we see BP, we're talking about boiling point, not blood pressure. The general rule is as you increase the surface area. So as they have more and more surface area, you're going to increase the boiling point. There is also, as you increase the branching, so the side group, you're going to decrease the boiling point because that's going to decrease the surface area. An example of that is if we compared pentane. Actually, if you go back to the previous page, so pentane and then that isomer we made, these guys both have 5 carbons and 12 hydrogens. So they have the same number of carbons. This one's going to have the higher boiling point because it has more surface area. So anytime you have more surface area, you have a higher boiling point. And that is something that has to do like this guy can keep stacking. And this guy, it's like condensed into a little ball. It doesn't stack up so well. And so that's going to create more attractions. And it's going to be harder to overcome that. So the general rule is that surface area piece. You'll see some questions in the homework and you just compare the two and we'll go through it when we go through the homework. All right, solubility, that's what your lab this week's about. And anybody want to answer that one for solubility for everything we did today, which is carbons and hydrogens, and why? And actually, I guess I should clarify that. Usually when we're talking about solubility, we're asking about water solubility. And these guys, the answer is nope. And that's because they are nonpolar. And the word for that is, again, hydrophobic. These guys, there's nothing in them that is interested in water. So they are not soluble in water. What are they soluble in? They are soluble in each other. So they're soluble in other hydrocarbons. And that's why I split the class up for the different celebrations. So these first few weeks, we're just going to be looking at the hydrocarbons, getting the basics and stuff. And they are insoluble in water, but they're soluble in each other. And this is one of the big problems, like with oil spills, because oil spills are octane, and octane doesn't mix with water. But the ocean has a lot of movement, as we all know. And yeah. All right. So most of the other weeks we'll be spending like we'll do one class where we'll look at naming and different ways to name and looking at some of the basic properties. And then we spend the whole class looking at reactivity. So there is a piece missing here, which is reactivity. So you want to add that word to this, and it is not much. And that is why they become the fossil fuels, that these guys really don't react. They really have, in lab, we can force reactions, but they're really hard to do. Double bonds are very reactive. They are the most reactive thing. So next week is going to be all about reactions. Triple bonds, even more reactive. When you get oxygens, reactions happen. Nitrogens, reactions happen. These guys, there's nothing. They're just carbons and hydrogens. They're in their stablest form, and that's why they become fossil fuels. There's one exception, and that is combustible. And that is why we are in the combustion age. That's the whole thing with our lump of coal and king coal, is combustion means to burn. And so we're going to write a chemical equation. So you guys remember burning? I usually do a demo here. I could break into my mom's liquor cabinet downstairs. And you guys remember burning means we're going to react it with oxygen. So combustible means burn, baby, burn. It's going to react with oxygen. And what do we get? Well, it's the whole thing behind global warming is we get CO2 and we get H2O. Our bodies are also combustion engines. We tend to make out in the real world what's going on inside of us. In our bodies, it's like this 30-step, very elegant process where we break it down, then go through the Krebs cycle and break it down to electrons, our food, and then the oxygen just wants the electrons. In your car, it happens in one step. And so we've just created a huge amount of CO2. All right, so we have 8 carbons. We're going to get 8 CO2s. We have 18 hydrogens. You guys remember balancing equations? The good news is this is pretty much the only equation we're going to balance this term. And then when we get to the oxygens, we're going to get that fraction. There's going to be 25 divided by 2 O2s, or 12.5. Or you can double everything and say you have 2, 25, 16, and 18. So if you prefer, you don't like the fraction, you can also double them all. So in Chem 104, you learned from whoever your teacher was, like you spend a lot of time writing equations and balancing and stuff. We're going to see in organic chemistry, we approach the equations a little bit different starting next week. All organic compounds go through combustion. So typically the lab we would be going to in the next 5 minutes, you guys would be burning stuff and heating water. It was really exciting. You would burn stuff, you would get covered with black, you would all look like coal miners by the time you left, and you would be heating water, and you'd be measuring the temperature, and you'd be getting masses. And it was a lot of fun because you would get to work with each other, and you wouldn't have to listen to me talk. and copy stuff down, and you would make friends, and you would be working in groups of teams of 4, so you would get to know each other. And I desperately miss that part. So I hope that you have a lab partner, whether it's your dog or your little brother or somebody like that when you do your lab this weekend, and I hope you have fun. Global warming is this whole thing of the CO2s. So carbon dioxide, remember drawing the molecule, is a carbon with oxygens on each side. So the shape of it is just the right vibrationals that when sunlight comes to, right, this is the planet, sunlight comes through, it hits the earth, it comes back up, it hits the CO2, and it comes back again. So it has the effect of like a greenhouse, where the glass over the greenhouse, if you've ever been in greenhouse, my uncle lived on a farm and had a greenhouse, and I used to love going in there because it was so toasty warm. But it's a greenhouse because it keeps the plants nice and warm. But we've created this layer around the earth, and CO2, methane, CH4 is also really good at doing this, that it reflects the light back. And so we've increased the temperature. The change in the temperature, it's just more that the weather's become more unpredictable. And we saw that this year, like the fires and all that kind of stuff. The cause is humans. We are absolutely the cause of it, and the effects. I actually am making a slideshow for next week's lab where I talk about this. And so your lab next week, because we don't get to burn stuff, is you're going to be looking up innovations for how we can deal with this. Like there's a thing where they paint houses. There's a type of paint, and this is being used in a lot of places around the world. And this paint actually absorbs CO2. And so if all of our houses started to be painting in a way that could absorb it, we could be dealing with a lot of the problem that we're creating. And so, yeah. And then you're going to, in a couple weeks, wherever my syllabus is, and we'll organize this. I guess it's like in the 5th week, I'm gonna split you guys into 2 groups of about 10 students each, and you're gonna do like a 5-minute presentation of one of the cool innovations that you found. Like you might be like into this paint that reflects or absorbs CO2 or something, and you'll do a presentation telling us about this really cool innovation. And so we'll worry about that. I'll have more details with the lab for next week. There's also then a presentation in the 10th week, which will be a molecule, an organic molecule, and I'll have those details more also in the next week or 2. I did also want to point out that Martin Luther King's birthday, we don't have class because it's Martin Luther King's birthday. President's Day, we do have class. That happens sometime in February, but we do have class. I don't know why this says this here, so let's just cross that out. There's typos because it's me. Is there any questions before I stop and we get to end it early? And I will hang out for another half hour, 45 minutes. I'm gonna go ahead and stop. And